Alright, let me see. All right. Let's see. All right, so today I will be talking to you guys about waves. So, waves is the topic of the day. And so, yeah, I know it seems a little bit not really intuitive why we're learning about waves, especially in a classical setting when we're learning about electrodynamics. But I guarantee you that you'll see the big picture at the end of the course and how waves are related to electricity and magnetism. But in order to actually start talking about it, you have to figure out what a wave is. Well, a wave is any object that oscillates within time and space. So we have our function, we'll call it, okay. So we'll call it y of t of x and t. So y is a function of both x and t to be a cosine or sine. All right, let's just do sine. We'll do sine because it'll be easier when computing derivatives. Sine of kx minus omega t is the most basic form of a wave you can get. And if we plot this out, we'll see that as y increases and as x increases, you'll have an oscillatory movement over a certain time period. So since this plots over x, over a certain amount of distance that you move, you will repeat your wave. And so that's not really anything. So yeah, that's not really anything new, besides the fact that you could write a wave as this form. Now, you're wondering, what is this omega that I drew, and what is this k, and why is it useful? Well, since we're talking about functions, a function that oscillates in time, which means it repeats itself, means that there is a certain point in time and in space where this function repeats itself. And in order for it to repeat itself, you would define that as the period. The period in the time sense, period t or tau, is equal to the time it takes to complete one cycle. So if we plotted this in terms of t, we would get the same thing, where here is the period. Because on this part of the branch right here, it's the same thing. This is the same waveform here, only over here, and it's at a different period. It's at a different amount of time. But this time interval, tau, is the same. It has to be the same, since this thing oscillates. And so that would be the way to define how this function comes back to itself in time. How it comes back to itself in x is known as the wavelength. The wavelength is equal to the length of oscillation. So if we look back in this graph right here, since this is a function of x, a function of distance, this wavelength is here. The length of oscillation, how far does it go before it repeats itself? And then the equivalent of that is lambda. And so how do we actually get these values and stuff? for that? Well, if we look at our function, let's say we set x equal to 0. So we're just investigating the time component. And so by setting x equal to 0, you have y of t now, which is equal to a sine omega t. Now, for a sine function, you know that this thing starts at 0 and it ends at 0. For sine of 0 at t equals 0, sine of 0 is equal to 0. So, with that being said, we know that through one oscillation that your function has to go back to itself, and it has to go back to 0. In order for it to go back to 0, you have to solve for what values of sine would go back to 0. So omega t would have to be equal to 0. Omega t would be equal then to what? Well, sine is 0 at intervals of pi. So sine equals 0 at t equals 0, t equals pi, t equals 2 pi, which ends up being n pi. So omega t is equal to n pi. What if we're just looking through, let me pull this up, and you know through one period, just like right here, one period, this ends up actually going through, here is n equals 1, n equals 0, because it's at the start. Here's n equals 1, and here's n equals 2. Which means that in one period, like we said, in one period, in the time it takes to oscillate, this would go through, omega t would have to be equal to, sorry, I'm going to write this over here, omega t would be equal to 2 pi in one period, right? It goes back to 0 through one period. I know I keep repeating myself, but I just want to reiterate, which means that at one period, our time is equal to tau, or it's equal to our period, how long it takes to repeat itself. So omega tau is equal to 2 pi. And once again, we can define what our period is. Tau is equal to 2 pi over omega, or this constant that tells us how fast it's moving, how fast it oscillates through a cycle. Well, you know that tau, the period, 1 over tau is equal to the frequency, is equal to number of cycles per second, which means that you can flip this equation and say 1 over tau is equal to frequency, which is equal to omega over 2 pi. And so the angular frequency, or the omega component, is equal to 2 pi f, which you guys should already know. That tells you how fast it moves. That tells you how many cycles it goes through per second. And that would be your component right here. And just to make sure things work out, this is in units of radians per second. In order to evaluate any trig function, you need units of radians. So when you put in sine omega t, omega is in units of radians per second times seconds from this time component is equal to radians, which means that your function is good to go. Everything works out perfectly. Now for the distance function. We said that we have sine of kx minus omega t. A sine kx minus omega t. Now, we said in time you could have oscillation in time. There are certain periods, or there's a certain amount of time where the function will repeat itself, which is known as its period. In space or in distance, when t is equal to 0 and you have y as a function of x, you'll realize that you have the same thing. You now have a sine kx, and kx must repeat itself. And it repeats itself over what we call lambda, or the wave height. Now, what is this k that I'm talking about? Well, in order for sine to repeat itself, it starts at 0, y starts at 0, and ends at 0, which means you have to find what values of sine is equal to 0. And that is at what? Well, we already said 0, pi, 2 pi, n pi, which means that kx is equal to n pi. Now you already know, going through here, it goes through, once again, it goes through two different zeros. Here's n equals 0, n equals 1, n equals 2. In order to repeat itself, you see that it goes through n equals 2. So kx is equal to 2 pi. Now we're evaluating only for one period, which means in a period we define this function to move through a distance lambda. So we set x equal to lambda, and then we get k lambda is equal to 2 pi. Oh, man. K lambda is equal to 2 pi, then we can define k to be equal to 2 pi over lambda. K is known as your wave number. So this is equal to the wave number. And now we know almost everything about our wave. We know that we can measure our lambda, we can measure when it repeats itself, or at what distance does it repeat itself, that's what lambda is. And we know that we can measure the time it takes to repeat itself, which is the period, or 1 over the period gives us our frequency. Gives us our frequency. Gives us our frequency, which we can use back in our original equation. And so, the last thing to note is, what is this a value that I wrote? Or two things. What is this a value that I wrote? And what is this minus sign? Well, I'm going to start with the a. So, you know for any sine function, sine always has a range from 0 to 1, or from -1 to 1. Sine is maximized at 90 degrees or minimized at -90 degrees. And so with that being said, in order to maximize your function, you need to evaluate this at pi over 2, which pi over 2 radians is equal to 90 degrees. Which means that a sine of pi over 2, sine of pi over 2 is always equal to 1, which means that y is equal to a. It's always equal to its maximum. So a is always the maximum. A is known as the amplitude, which tells you to what extent does y reach. Y will ever always reach a maximum value of a or a negative value of a, which we could see back in our wave. Here's positive a, its maximum value where it reaches, and then it comes back down, and it goes to negative a, its minimum value where it reaches, which means that a tells you to the extent of what y how y moves. And what's very useful about that is because you could find other properties about maximum values. So let's say we already have our function. You'll see what I mean in a second. Second is equal to a sine kx minus omega t. And so y is your displacement in the y direction. If you want to find the acceleration in the y, dy, or the velocity in y, how fast it's moving in the y, take the derivative. Dy dt is equal to velocity. Yeah, meters over seconds gives you velocity. It's equal to a sine. Now we're taking the time derivative. So the time derivative of this means that, derivative of sine is cosine. Now we're taking the time derivative. So taking the time derivative of this argument means kx stays constant. Kx stays constant, so that differentiates to 0. And negative omega t differentiates with respect to time to negative omega. Which means that y prime, or I'm going to write dy dt, since this is actually a function of 2. This is a function of 2 variables. So dy, the partial of y with respect to t, is equal to vy, which is equal to negative a, I'm going to bring the omega in front, cosine kx minus omega t. Which means that we can look at this a number amount of ways. The velocity, one, the velocity is negative for this function, and 2, this term right here, a omega, is now equal to the maximum amount of velocity. Now, this thing is maximized when cosine is equal to 0. Cosine of 0 is equal to 1. So when this argument right here is equal to 0, which is initially at the start, x equals 0, x, which is at the start, x equals 0, y equals 0, t equals 0 gets you 0. So a omega is equal to v max. Now let's see if that's true. If you look back at our function, if you start here and you want a path like this, in order for you to move yourself up along this sinusoidal wave, you need to, well, have some sort of kick. You need to have some sort of go, which is equal to a omega. A omega tells you that that's your starting velocity, and at t equals 0, you have a non-zero velocity, which means you have a tendency to move up. And And once again, if you take the last derivative, if you take your acceleration, which is equal to dv, we're going to do partials again. Because we have a function of x and y, d squared y dt squared is equal to, well, we'll just differentiate our velocity, is equal to d dt vy, which is equal to, well, the derivative of cosine is negative sine, so you have negative a omega negative sine kx minus omega t. Now, the derivative of negative omega t is just negative omega. And so this gives us what? This gives us a omega squared sine kx minus omega t. Not 2, t. Omega t. The minus sign in front. Now, what does that tell you? Well, it tells you two things. If you're really savvy in math, you'll realize that if velocity and acceleration have the same sign, then this thing give me 1 second. That this thing accelerates. And in fact, it does up to that point. So I will show you why. Since this sinusoidal wave is periodic, it means that it repeats in both directions. Which means if you're at a point right here and you're at your minimum velocity, which is negative a omega is equal to v min, and your acceleration is the same sign, that means that you're going to accelerate. You're going to increase velocity. V must increase. Since the signs are the same. Since the signs are the same, v is negative here and acceleration is negative here, then it's going to move in the same direction, which means it's going to move, or which means it's going to accelerate, which means that going from a negative velocity, going from negative a omega, you will increase to 0, right? This negative value is less than 0. So if you're increasing your velocity, you're going to go up to 0. Well, hey, check it out. At this point right there, sine is maximum. If sine's a max, you're at maximum displacement. That means, well, the derivative, which is velocity, cosine of, when sine is max, cosine is minimum. That means velocity goes to 0, just as we suspected. And so, yeah, you could do some pretty neat things with this. You could find out that the maximum acceleration then is equal to a omega squared. So, we put absolute value. Because like it said, it could be positive or negative depending on which direction it's going. And so, since this is the amplitude of your acceleration function, a max is this, which is a omega squared. All right, so we dissected the properties of the waves, except for one thing. Why did I write the wave as this? A sine kx minus omega t. What is this minus sign? Well, this minus sign, let's check it out. If this is our sinusoidal wave, and yeah, if that's our sinusoidal wave, and I can move out this negative sign to give us this. A sine negative kx minus kx plus omega t. And sine of a negative number is always equal to its opposite, which gives me a sine, I'm going to bring omega in front, omega t minus kx. Which tells us that if you move positive, which tells me two things. One, if I set x equal to 0, then in time, this becomes a function of time. You have a sine omega t, which tells me this. As t increases, sine becomes negative, which tells me that instead of moving like this, I'm actually moving like this. I'm actually moving like this, because negative sign is just a reflection. Well, if you look closely, if you put a map of the two together, you'll see that this was our first direction, and if we draw two waves together, that's two cycles, but one's going in the negative direction. One's in the negative x, and one's in the negative t, and one's in the positive t. We have a waveform that looks like this, which means that this is how the wave travels. The wave moves this way. Therefore, if omega t is negative, then you know that this thing travels to the left, because that is the exact mirror image of a wave, but that's only moving in the negative y direction, in the direction that goes opposite of time. Which means then, if we look back at our original equation, a sine kx minus omega t tells us as time goes forward, the wave moves backwards. Appears backwards. Now let's look back at what we had. So I took out the negative sign. So that's for just time. If you're just looking at the time component, that tells you that, yeah, negative omega t runs backwards. It makes it look like the waves move in the opposite direction. If you're just looking at the time coordinate, let's look at the x coordinate. So we have, if I'm rewriting our equation, when we pulled out our negative sign, we have a sine negative kx. And we're going to set t equals to 0 now, because we're just looking at the x component. Now, once again, sine of a negative number would just pull out another negative. which means that we have negative times negative a sine kx is equal to a sine kx. Okay, and since a sinusoidal wave moves like this in the positive x direction, and since our x's now are defined to be positive, if our x's are positive, then you know that, yeah, in order to get this waveform, the regular sine function that we all know and love looks exactly like this. In order to get this, x must be greater than 0. If x is greater than 0, that means the wave moves in this direction. The wave moves in the positive x direction. So what we can dissect from this is y of x comma t is equal to a sine kx minus omega t. If someone asks you what direction is it moving, well, what direction it's moving in space, well, you know, once again, if you have a negative sign right here, if you have kx minus omega t as your argument, you know that this thing moves to the right, or positive x direction. And it's that simple. And if you're really good at math, you'll also notice that if you have a function, just like a parabola, if you actually have a function x minus 1 squared, this is actually centered right here in the positive x direction. A negative sign in an argument always means that it's shifted over to the right. If you had x plus 1, this is actually shifted over here. Same with sine. If this argument is negative, then you know that it's shifted to the right. If this argument is negative, or if this argument's positive, it's shifted to the left. And so if you guys just want to see that, I'll do that really quick. Then we have now, if you want to see that, we can take out another negative sign. Negative kx Oh, no, I don't have to. That's not needed. And I'll show you why. Since we already proved that, I did it implicitly. And I'll show you what I mean. If we just look at this component right here, you see a sine kx tells you the direction it's moving. If you have any positive x value, this sine function will always move to the right. It will always be positive, correct? It will always be positive if this argument is always positive. Let's say you're moving in the negative x direction, so you tack on a sine of negative x. Then this function will become negative a sine kx, which means that it will move this way. So if you just stick a negative x inside here, you'll get that it's moving the opposite way. If you stick a positive x in there, you'll see that it's moving in the positive direction. And so it's not. So that proves to us that, yeah, if the argument is negative, so if moves in the positive x direction, and if kx, you have kx plus omega t, it moves in the negative x direction. Pretty neat stuff. And so yeah, you could do a lot of good things. You could do a lot of things. A wave equation tells you a lot of things. And it tells you specifically what is the velocity of the wave. Now, earlier when we started differentiating, we said that we differentiated y with respect to time. Well, that's finding how fast the wave moves in y. To find how fast the wave is moving in general, you'll see this. If we look at velocity is equal to meters per second. The velocity of a wave in a certain cycle would be the distance traveled over the time it takes. Which means that in one period, which means that the distance traveled in one period we defined already as lambda. We defined one period to be tau, the time it takes for it to recycle. Well, more conveniently, it's lambda times 1 over tau. Now, 1 over tau is the frequency, or how many cycles per second. Lambda f is equal to velocity. And it's that simple. Velocity of the wave. You might be saying, oh, what if you have, is the velocity consistent throughout the entire thing? And yeah, of course it is. If you move through 2 cycles, if that's 2 cycles, that means your period is 2 tau. And then your wavelength is lambda and lambda, which means that v is equal to 2 lambda over 2 tau. And it factors out, and the velocity is consistent throughout, which is very nice and reassuring. And so, yeah, that would be the velocity of the wave. And you could be fancy and figure out, oh, well, you might notice that lambda f isn't really intuitive. I have a wave equation and I have a sine kx minus omega t. And I don't see lambda or f in there. Well, let's take it slow. Lambda is equal to, well, k is equal to 2 pi over lambda. So lambda is equal to 2 pi over k. Now, omega is 2 pi f. So f is equal to omega over 2 pi. If you do v is equal to lambda f, you'll see that you have omega over 2 pi, which is frequency, times 2 pi over k. This is frequency, this is wavelength. 2 pi's cancel, and it's equal to omega over k. And omega over k are constants you already know. They're right here. They're given to you in your equation. And it's that simple. And so another question that might come up, just for doing the homework, is what is the average? What is the average velocity? Well, in one period. Well, you know that a wave travels like this. In the same case as above, a wave travels like this. Now, the average velocity is the average velocity that it sees through a cycle, which means it's the average Vy. Now, the average Vy can be found by, like we normally do. V is equal to distance over time. Now, you see that the y, if you're moving in the y direction, you move like this, which means you actually move up like this. Going up to this peak, you move up there. That's 1 unit of A. Remember, A is the maximum y displacement you could have. To move back down, back here to y equals 0, you move another distance A. From going from 0 back down to this bottom crest, you'll have another A. And to move back up to 0 to complete one cycle, you'll have another A. Now, how many arrows did I draw? That's equal to 4 arrows, which is 4A is equal to your distance. And once again, this is for one period. So your velocity average in the y direction is equal to 4A over tau, because the average velocity is your average distance over the amount of time it took. You went up a unit A, down a unit A, back down a unit A, and then back up to get to 0. So that's 4 units of A you moved. And you divide by tau because that's how much you move in a time, or how much you moved within a period. And so when you're working out problems in your homework, there's really nothing too complicated about waves, other than just knowing the general form, knowing which direction it moves. Depending on the argument, if it's positive or negative, you'll know what direction it moves. Depending on what values are stuck to x, will tell you wavelength. What values are stuck to y, or stuck to the time, gives you frequency, period, and a combination of the two. Once again, omega over k gives you the velocity of the wave. But if you want the velocity of the y direction, you'll take. If you want the velocity of the y direction, you'll take the derivative of your function with respect to time. If you want the acceleration, take the second derivative. And with that being said, if you take the acceleration, you could find properties about y. You could find acceleration and some sort of force if you're given a bead that moves along, your path. Since force equals mass times acceleration is equal to m d y squared dt squared. Well, you could solve this. And if you have a bead that's moving like this, where your bead moves along here, you could find the force. The force is just mass times acceleration. And another thing related to the force is the tension. It might ask you, what's the tension in the rope? Well, if you recall, B is equal to square root of T over mu, where mu is equal to the density. And the density for a string, since it's one-dimensional, is equal to mass over length. So in order to solve for tension, you need to solve for V squared mu. It's equal to tension, sorry. And in order to find your velocity, once again, you need the velocity of the wave. V of the wave is equal to what? Omega over k is equal to lambda f. Lambda f squared times mu gets you the tension you're looking for. And to be honest, that's basically it with your homework, I believe. It's all you could really do about waves until you, at least classical waves, until you will learn how to apply electromagnetism to these classical waves, and you'll solve other problems with them. And you should be doing that sometime soon. So thanks, guys. That's it for the lecture. So see you guys in class.